Hi, everybody. Today we're going to go take a look at the Smith College power plant. This is a great opportunity because here at Smith we make all of the heating and cooling and electricity for the whole campus in our own power plant. So if you're interested in mechanical engineering or electrical engineering, if you're interested in carbon policy or energy policy, or if you're just interested in cool, big industrial things, we have them here on campus and we can explore them. So before we go down and take a look at the plant, we're actually going to do a quick overview of how some of these things are made so that when you see the pictures that we're going to take down in the power plant, you understand what you're looking at. So to start us off, let's talk a little bit about heat. So one of the things, Smith has about 114 buildings, and we need to keep them warm because apparently it gets pretty cold here in the wintertime. And in the winter, if we let the buildings get cold and suddenly things froze, that would be really bad. So it's good to keep things warm. It's good to keep students warm. It's good to keep pipes warm. And to do that, essentially, there is an open flame somewhere. So we are burning fossil fuels. In our case, it's a lot of natural gas. There's an open flame inside of a box. Some people call that a furnace. If it's a furnace, typically it's being used to heat up air. If it's a boiler, it's either heating up water or it's making steam. In our case, we're making steam. So there's an open gas flame and it's heating up water in a bunch of pipes, and that water is turning into steam, and the steam is what gets distributed all the way across campus. On the left, you'll see this is a map of campus that shows where those steam pipes go. So this is the power plant down here at the bottom of the hill behind the ITT, and there are pipes that run all the way up along right here to the corner in front of Tyler House, and then it splits. One arm goes this way and eventually across Elm Street, and the other arm comes up past the Botanic Garden and then all the way around to the quad. So there's steam, pressurized steam is pushing up through those pipes. It gets to a building. It releases the heat and its energy. And when steam releases its energy, it turns back to water, which we call condensate. And that condensate rolls by gravity all the way back down the hill to the power plant. And we'll show you in a minute where that condensate gets pumped. So on the right, this is a picture of the construction of the steam tunnels. That's from 1946, and that's right in front of the alumni gym. This is the old Nielsen Library, right at the end of that tunnel, and this is the construction of that system. Before the system went in as a district system, we were heating every single individual building through its own boiler with either it was coal-fired or it was wood-fired. So the other thing we do down at the power plant is we make electricity. And just to keep this extremely simple, to make electricity, in almost all cases, you need some rotational force. You need something spinning. And you spin magnets and copper against each other in order to generate a current. So you can see here, we have a magnetic field, we've got coiled wire. When you spin those things against each other, we get an electrical current. So typically you need something creating that rotational force, and that's usually turbine blades. So turbine blades are kind of like fan blades. So something has to be pushing against those blades in order to be creating rotational force. Most often, most places around the world, it's steam that's pushing on those blades. So water was heated up using an open flame, it made steam, and the pressurized steam is pushing against those blades. So that hot water can come from coal, it can come from natural gas, it can come from wood. But if you think about the fact that to make electricity, we just need rotational force, something going around and around, right? This is how we understand how we're making wind power. The wind is pushing on those blades and spinning an axle, which is making things go around and around. In this case, this is a cutaway of a hydropower facility where the pressure of water is pushing on blades. It's making something going around and around. And this is a set of exposed blades from a nuclear power plant. So in that case, we're cracking atoms. It makes a lot of heat, which boils water, makes steam, and steam presses on blades that look like this. There are, maybe there are other untapped sources of rotational force. People always say that cats land on their feet, and people say that toast always lands butter side down. So if we strap buttered toast to the back of a cat, maybe we could have a perpetual motion machine. One big exception to rotational force, which is solar power. So obviously there's nothing spinning around here. This is the roof of the ITT, and there's Ford Hall. You can see PV panels on the roofs of both of those. And in that, solar power uses the power of the sun on a substrate of silicon, and through a miracle of physics and chemistry, it flicks off electrons and we get electrical power. We're not going to go into the details of that, but it is an example where we don't have rotational force. Okay, we've talked about heat, we've talked about electricity. So what happens when we put them together? In most cases, to make both of them, we need an open flame somewhere. So our power plant is what's called a cogeneration power plant, or a combined heat and power facility. So in our case, we have a turbine generator. It's essentially a jet engine. A jet engine sucks in air, and it takes compressed fuel and it ignites them together. So you have an open flame. You probably didn't realize this, but inside the jet engine, there is an open flame. And that open flame, that reaction of the air and the fuel and being ignited, creates an enormous amount of thrust. That thrust pushes on blades, which makes something go around and around, which makes electricity. Out of the back end of that jet engine, we get about 1200 degree Fahrenheit exhaust gases, really, really hot. So we can make steam at the same time. So think about it this way. If you're just making electricity from coal, and I'm heating up the coal, I'm lighting the coal, and I'm making steam, and I'm making electricity, that system is only 25 to 35% efficient. You're only getting 35% of the power out that you put in. In a heating system, in a home heating system, you're lucky to get about 90% of the fuel energy you put in come out as heat. Neither of those systems are perfect, but if you're imagining that we're using that same open flame, and we can get the rotational force and the heat, we have a much, much more efficient system. So let's talk about that efficiency. When you only are getting 33% out of a coal power plant, where's the rest of the energy going? Well, we could say, what is this cat doing? If you've ever seen a cat sitting on the hood of a car, that's because it's warm. Where's that heat coming from? That's wasted heat. That's wasted fuel, right? Instead of making the car go forward, which we would call an energy service, some of that energy went into just the creation of heat. Now, that heat is an energy service to that cat, but from a transportation perspective, that's rejected energy. It's just wasted energy. And our world is full of wasted energy. This is a chart that the kind people at the Lawrence Livermore National Laboratory put together. And it's all of the energy inputs and all of the energy outputs for the entire US economy. And I can just say I've seen these for Japan and for other places around the world, and they more or less look the same. So what we're seeing is, on the left, these are all the inputs. The biggest inputs are petroleum and natural gas and coal, right? And this is roughly in percent, because the nice thing is this is about 100 quadrillion BTUs of energy. So we can sort of think about these things almost in percentages. It's about 40% petroleum, 13% coal, 30% natural gas. Solar right now is only about 1%, but growing, right? hydro is about 2.5%, nuclear is about 9%. So those are all the inputs, and they go through this spaghetti diagram. 38% goes into electrical generation, and then these other sectors, right? Transportation, industrial, commercial, residential. There are two things that come out. Energy services, about 32%, and rejected energy, 68.5%. So that rejected energy is an enormous quantity. If we could take back just a little bit of that rejected energy, we could eliminate all the coal inputs into the system using no new technology to generate electricity or heat or services just through efficiency. So cogeneration is a really great energy efficiency measure. And in fact, when we installed the cogen power plant at Smith, we dropped our carbon footprint by about 30%. So significant improvement in environmental impact. So now we're going to go take a walk across campus, and we're going to go down and take a look at the power plant.
You might wonder what the power plant has to do with your journey here at Smith. So let me give you a couple of examples of ways that students have fit the advantage of having a facility like this into their work. One example is we currently have a number of engineering students who are working on helping us plan the future of what this system might look like. How will we provide heating and cooling and electricity to campus without carbon emissions? And they've been working on questions like battery storage in the future, and they've been thinking about and analyzing the ways in which we use heat and energy on campus now. Another example is that we've had students who are interested in history look at the history of the system. We had one student who went ahead and looked at the decision that the trustees made in 1947 to build the system that we have now. She learned through her research that the trustees had made this decision based mostly on financial considerations, but also significantly on considerations of the pollution of ash and smoke on campus and the removal of ash from campus buildings. So we learned that there were both financial considerations and pollution considerations that came into play in 1947.
Hey everybody, now we're standing in front of the Smith College power plant. This is where we make heat and electricity. It was built in 1947, and it was built with just the idea of making heat in mind. We're going to go inside, we're going to take a look around, and I'll show you some of what, in real life, some of the things that you saw on the presentation earlier actually look like.
Hi, I'm Chuck Doherty. I'm the manager of the cogeneration facility here at Smith College. Glad you could be with us today. Thanks.
So when the power plant is running, when we're making steam or we're making electricity, there are two plant operators here around the clock. So all the time, 24 hours a day, there's always two here for safety reasons. And they monitor the system using a screen like this. This one actually looks at electricity. And so what we can see from this is our own turbine, and right now we're making 0 kilowatts. So the turbine's not running. We're importing all of our electricity. And that's this number right here. So right now we're importing about 2,500 kilowatts. So it's also 2.5 megawatts of electricity. So as we mentioned before, Smith distributes steam around campus, and that's how we move heat from this building all the way around campus, all the way up to the quad. The pressure of the steam moves it through the pipes. When it gives up its heat and loses its energy, it turns back to water, what we call condensate. The condensate flows by gravity all the way back down the hill to this building into the basement. These are pumps. The pumps pump the water out of the basement and back upstairs where we make steam again. We lose a little bit of water in that process, so we also add water here, and we process that water, we soften it and take the minerals out. Because as you boil water, if it has a lot of minerals in it, those minerals come out and they can really clog up the system. Be very careful, high voltage. Now we're going to the electrical part of the power plant.
So behind me, this is what we call switch gear. It's kind of like the fuse panel or breaker box in a house, except these are really, really huge electrical switches. So we both control the electricity coming to campus from the grid and the electricity coming from our own turbine and how it feeds the campus and whether it enters or exits the external grid. So Smith can import electricity from the grid if we need more, or we can export electricity to the grid if we're making too much. So we have a lot of flexibility. If the power goes down in the external grid, we can go into what we call island mode, where one of these big switches opens up, which means it gets interrupted, and we can serve our own campus with electricity. So it makes us much more resilient than we would be otherwise. So typically, if the power goes down in the outside grid, our turbine switches over automatically, and if you were on campus, you wouldn't notice the difference between running with the grid on and running with the grid off. So the grid goes off, one of these big switches opens, and our power plant takes over. Sometimes it's possible that our turbine can stop operating. If we do, and there's no outside power, you need to have enough power to start up the system. So this is one of the interesting things about all electrical grid systems is you actually have to have some electricity to start the system running. So there's two things in our power plant that give us that resiliency. One is this bank of batteries. These batteries just provide enough electricity to the bank of switches that I showed you earlier, just to allow them to operate. Once they're operating, then we can start up the turbine. And we do that using a separate generator. So the turbine and the electrical generator, it's essentially an electric motor. If it's operating one way with the current going one way, we're making electricity. But you can use that electrical generator to start the turbine spinning. So we need electricity to start the turbine spinning, and then we can add the gas and essentially light it. And then it can operate on its own and it will make electricity. So it's a combination of these batteries and a very large generator out in another building that allow us to what's called black start, or start from when there's no electricity either on campus or in the grid. So this is the generator end of the cogeneration system. So the rotational force that the turbine is creating, and that axle comes all the way up into this space right behind the Smith College emblem. And this is where the electricity is made. So again, we have magnets and copper coils that are generating electricity, and that electricity is going out through this line. This is the turbine engine. This is sort of the heart of the cogeneration system. It's essentially a jet engine. And the way that a jet engine works is there's compressed fuel. In our case, it's natural gas. It's put through a compressor. And there's air is compressed by the front end of the fan. And I'll show you an image of this in a minute. But air is brought in, it's compressed, it's mixed with the fuel, and it's ignited. The ignition of that fuel and air mixture creates an enormous amount of force. That force essentially pushes on fan blades, which creates the rotational force and the spinning that we need to turn the generator. The generator is that way. That way is exhaust, and we'll show you where the exhaust goes. So, as the turbine's running, all of that hot exhaust is coming out this end. It's going into this set of ductwork. It's turning a corner, and it's going upstairs to the exhaust system. So we're going to show you that in just a minute. So now we're upstairs. Downstairs we saw where the exhaust gases exit the turbine and turn the corner and go up. The first thing that happens to them is they pass through this system, which is a treatment system. So in addition to carbon emissions, when you burn natural gas, you get other emissions like oxides of nitrogen.
Oxides of nitrogen contributes to low-level atmospheric pollution, things like smog, so traditional smog. At this location, ammonia is sprayed into the emission stream, and that ammonia reacts with the oxides of nitrogen and neutralizes them chemically. This is a regulated process, so we have an air permit with the Massachusetts Department of Environmental Protection, and they regulate and watch our treatment system. So this is the stack that exits the building. The treatment is down below, as I mentioned. Up above, in that sort of gray box, is what's called the heat recovery steam generator. In that unit, that's where the hot exhaust gases, which are about 1200 degrees, pass through a set of tubes that have water, and there's enough heat there that water is turned to steam. This is a cutaway view of the turbine engine downstairs that we saw. You can see these fins here are the fins that pull in air. When this whole thing is spinning, it's a fan. It pulls in air and it compresses it as it moves across these fins. This is where it's mixed with gas and ignited. And then this is where the thrust is happening. And this is these fins here capture that thrust and create the rotational force. A jet engine is almost identical, except it doesn't have these, it has fewer of these fins. Because a jet engine, you're trying to optimize thrust over rotational force. Here, we're trying to make more rotational force so that we can make electricity. Okay, behind me, this is a boiler. Smith has 3 large boilers that also feed the heating system. So we talked about the heat recovery steam generator. That's what we try to use first, because that way we're really taking advantage of the higher efficiency of cogeneration. We have one flame, we're making electricity, and we're making heat. That heat recovery system provides about 20% of the heat that we need on an annual basis. On the coldest day, it's maybe providing about 1/3 of the heat we need. So over the course of a year, we need more heat than the heat recovery system can provide. So we have boilers. Sometimes we call them peaking boilers, but essentially they do the same thing, which is it's a series of pipes, and there is an open flame that is heating up the water in those pipes and turning it to steam. This is a very large boiler. This is our largest boiler, and it can heat campus by itself. Without cogen running, without any of the other boilers, there's enough capacity here that it can heat all of campus. So even though we have one big boiler that could heat all of campus by itself, we have a lot of redundancy in the system. We have 2 of these boilers. These are from 1972, and they are smaller than the last boiler we looked at. And together, the 2 of them could heat all of campus. So we are always prepared for if something goes down, then we have another way to keep campus warm. There's really nothing more important than if the power goes out, if the gas is interrupted, that we have a way to keep buildings warm. If we can't, then all the water freezes, and we actually have catastrophic losses. So we have a ton of redundancy built into our heating system. If the natural gas system is interrupted for some reason, these 3 boilers can also burn number 6 fuel oil. We maybe do that for 1 or 2 days every couple of years when there's not enough gas in the gas system. But that's it. Prior to cogen being built in 2008, we used number 6 fuel oil all the time in 5 boilers that were at this location. So these 2, they're from 1972, and 3 older ones from the 1950s that have since been removed. Okay, so this is the main control room here in the power plant, and as I mentioned earlier, there are 2 people here whenever we're making steam. So if the generator is running or we're making steam with the boiler, there's always 2 firemen here at all times. So remember, on a cold night in the middle of winter, there's always somebody here in the power plant making sure that campus stays warm. So thanks for joining me on a virtual tour of the Smith College power plant today. And you can always follow up with any of us in Seeds if you have questions or you want to learn more.